all of you.
Yes, sir. Visible. Visible. Very.
Madhukar, if you have started recording.
Yes, sir. Yes, sir. I have started.
Okay, thank you. Okay, so today's session is about Open RAN. So you might have heard a lot of hype about Open Radio Access Network. Everybody talks about that, and there are many organizations which are working on Open RAN. So what exactly is Open RAN? Which are the organizations working into Open RAN, and why operators are interested in Open RAN? So all these aspects we'll try to cover. It's not this topic is not deep technology, but the concept wise we'll be talking about. Okay, so first let us understand about the basic concept of traditional RAN, traditional radio access network, vRAN, virtual radio access network, and then Open RAN. These all are a different terminology which is exist in this scenario. So Madhukar, if you can mute others, that will be good. Okay, so what is a traditional RAN? As you can see in this picture, during our earlier era of 2G or 3G or even at 4G, we used to have like BTSs, base transceiver, uh, located at a place where we have a tower. So on top of tower, we have antenna, and below the tower, either in a air conditioned room or in a outdoor setting, so either indoor or outdoor, we used to have a box called baseband unit, and it was also having the radio unit part. So antenna is on top, BBU and radio was at the bottom, either in a indoor air conditioned environment or in a outdoor environment. And the connectivity from this BBU to the antenna used to be through RF cable, waveguide, if you recall. So this was the traditional RAN. So later on, what has happened is, like, if you use a waveguide, so generally there will be a loss, and the average loss may be uh, at the level of 2 dB. So to avoid this, what industry did that the RU part, they took to uh, near to the antenna, either part of antenna or just below the antenna. So RU was shifted from the BBU to top of the tower near to the antenna or part of the antenna, and the BBU remained at the bottom. And this cable now became fiber. Instead of waveguide, cable from BBU to this become fiber, because RU part is up. So waveguide was not required, it is fiber. So the 2 dB loss which was there was actually reduced. So some energy efficiency came into it. So whatever we have on the top is nothing but a RF part. And basically, as you know, that digital to analog conversion, analog to digital conversion is done at RF level. So, and the below, if you look at the interfaces and the hardware, so the RU hardware traditionally used to be a proprietary hardware. That means if Nokia is supplying the equipment, entire equipment will be supplied by Nokia, baseband and RF, everything. The baseband hardware was also proprietary, and baseband software was also proprietary in a traditional radio access network. So both the RF hardware is proprietary hardware, baseband software is proprietary, and also hardware is proprietary. And the interface on this fiber, the interface which is running is called CPRI. CPRI, you might have heard. So this interface was also proprietary interface. So everything was proprietary in traditional RAN. So that means if you are like buying equipment from Nokia, you have to always buy equipment from Nokia. You cannot have mix and match of different vendor. So kind of a vendor lock used to happen in traditional radio access network. Then these OEM started promoting something called virtual RAN, vRAN or virtual RAN. So virtual RAN is not really open RAN. So in virtual RAN, what they're trying to do is the same traditional RAN. What they're trying to do is that this RF will remain proprietary hardware as it is there in the traditional RAN. But the BBU part, the hardware is becoming COTS hardware, commercially of the self hardware. That means this can be any server. And the BBU software, which handles physical, MAC, RLC layer, etc., is still proprietary software. But the interface part, this interface is also proprietary. So what has opened in virtual RAN is that BBU is virtualized. That's the only thing which we're able to do, that the BBU is virtualized and can be installed in a COTS hardware. So this concept is the virtual RAN concept, which many OEMs talk about, and this is not really a open RAN. So what is open RAN then? So we have talked about traditional RAN, virtual RAN. So what is open RAN? So in case of a open RAN, what is open RAN? In a very overall method, overall way, we can call this as a open RAN. So what I had changed, my RF is on open hardware and it is running software defined radio. Interface between BBU and RF is open. The CPRI interface is implemented in an open way. The COTS hardware for BBU software is still proprietary. So this is the open RAN concept which we have. Now just compare everything together. In our traditional RAN, where I have baseband unit below the tower and RF unit just below the antenna on top of tower. This interface is proprietary. This is a proprietary hardware, and this is also a proprietary hardware and software. Hardware oblique software is proprietary. This is proprietary hardware. In case of a vRAN, what changed was everything was proprietary, but the COTS, the BBU was virtualized. What was virtualized is the BBU by using a COTS hardware and software of BBU. So that was virtual RAN. And what is open RAN? In case of open RAN, RF is also open RF. Open has become the COTS based hardware. And then you have an interface also as open, and BBU is also virtualized. And of course, software is still proprietary, but COTS is virtualized. So this is the concept of open RAN if you compare everything. So that's the basic. Let's go slightly more into detail of these. Okay. So any question so far before I move to part 2? Okay,
Excuse me, sir.
Yeah.
Can you just once highlight what is that COTS?
COT is commercially of the self hardware. That is, if you buy a Dell server or IBM server and deploy the BBU software on that, so that is the COTS
Commercial?
of the self hardware or server. So basically what I'm trying to tell you that when you buy traditionally, when you buy a BBU, that used to be purpose built hardware and software, a separate box which has hardware and software coming from a particular company like Nokia, Ericsson, Samsung, Huawei, or ZTE. In case of a virtualized BBU, you can buy your own hardware, own server, maybe Dell server, and then Nokia can give you BBU software which you can install onto your own hardware. So that's COTS hardware or COTS server. Is that clear?
Oh, yes, sir. Thank you, sir.
Okay. And that is what is the concept in 5G, that all network element you can install in a open hardware or COTS hardware. Okay, now the second part of the session is about understanding what is centralized radio access network. Sometimes they call it cloud RAN, cloud radio access network, and you might have heard a terminology called BBU hotel, baseband unit hotel. So and this is also not really open RAN, but the OEMs have conceptualized this concept of C-RAN or cloud RAN. So what it is? So generally, as we saw that in a distributed RAN, we had kind of on top of tower antenna and RF part, and then we had the fiber where CPRI is running, and then baseband I have a BBU below the tower. Similarly, I have second tower, third tower, fourth tower, and they are being connected to the core. Okay, so these are distributed RAN. If you like break it, as I discussed, that below is the BBU, top is the RRH. Now, and the protocol is CPRI. This we have discussed. So, as we know that BBU handles all the radio protocols, right? BBU handles all the radio protocols, and then it forwards it to the core network. In case of a centralized RAN, what is happening is the BBU, instead of putting below the tower, that can be brought to a centralized place. Okay, so all these BBU from each of the tower can be brought to a centralized place, and then we can call it as a centralized RAN because the BBU is being centralized. Only the two things. One is the RF part and antenna. They are at top of the tower, whereas all the BBU I can take to a central location. And then I can have fiber to connect RF and this BBU at the central location. So this concept, since I have brought all the BBU together, so many a times some of the vendor call it as a BBU hotel because these are BBU installed at a central location, aggregated, and then traffic is going towards core. Now I have an opportunity that since these BBUs are centralized at one location, can I have a virtual environment? Can I have a virtual environment? Yes, we can always have a virtual environment. So that means I'm talking about this BBU to be virtualized. But before that, let's look at what is the advantage of having a centralized RAN. So one of the advantages which I see is like earlier at every tower location, I had to maintain air conditioning, space, battery, power plant, more capacity of battery and power plant, etc., which is not required to be done at so many sites because we have centralized at one location. So at one location, those aspects can be taken care in a better and efficient manner. Secondly, in case of any failure or any testing, one has to go to each site to look into, whereas in case of centralized deployment, those would be possible from one location. You can test all the BBU from one location itself, so it reduces the cost. Now, the next question comes to our mind is that how far I can take this BBU away. So in this picture, what you see is like these are the fibers and they are using the CPRI protocol, CEPS, CPRI protocol. And these are dark fibers. These are dark fibers. very high data rate is required. So we can maximum go up to 15 to 20 kilometer. There may be a question that why we cannot go beyond, because if you go beyond, the latency involved will make the working difficult. So it may not work properly. Secondly, the CIPRI protocol which has been designed may not be able to handle it also beyond 15 to 20 kilometer. So ideal distance is that in a city, connect all your BBU to one location in a 15-20 kilometer radius, you bring all the BBU at one location. So that can be a concept. So this is the concept of centralized RAN. So now, as I was talking, that can we think of virtualizing the BBU? So yes. So these I can, instead of individual hardware of BBU, I can try and have a server that I can virtualize BBU functionality and then deploy BBU on a virtualized environment, right? Okay. So basically, finally, this comes out to be architecture like this, that radio remote head or antenna plus RF is on top of antenna. Fiber is connecting this to a centralized BBU. We call it central office or BBU hotel. And this distance is typically 15 kilometer. We call it front haul, and the protocol follows is CPRI. And from BBU, I can aggregate and it can go to the core equipment backhaul. So this is the concept of TRAN. Now, why we are talking about Open RAN? What is the reason that we are trying for an Open RAN? So we are not trying to promote virtualized RAN only or centralized RAN only. We are talking about Open RAN where the interfaces are open. RF hardware is GPP hardware. SDR runs there. BBU is virtualized. BBU software can be proprietary in Open RAN also. So why we are talking about Open RAN? First is that majority of the cost of network goes onto the RAN. Almost 70 to 80% capex and also OPEX goes onto the RAN part. In case of 5G, when we have a small cell, a very large number of small cells, so this even goes beyond 70-80%. And finally, I mean, the promise of Open RAN is that reduction of the cost, as there is a possibility to develop a bigger ecosystem of OEMs, manufacturers, developers. So Open RAN may bring lower cost for operators. So that's why everyone is talking about distributed unit. Another is called CU, central unit. And of course, we have radio unit. So layer 1, 2, and 3, out of layer 1, 2, and 3, layer 1 and 2 say went to distributed unit, and layer 3 to centralized unit, and layer 3 we were able to deploy on a cloud infrastructure or virtualized infrastructure. And then finally we move to Open RAN, ORAN. So Open RAN standards are from ORAN Alliance. So we divided the product into a 3 product and also added certain other component. So what were those? So basically then we have an open radio unit having open front haul OFH. Generally it is eCPRI, enhanced version of CPRI, and it's an open protocol. And then we have open DU, distributed unit, which may be virtualized. Okay. So that means I can have ORU from 2 different companies, open DU from a third company, and this also interwork because it's an open kind of environment. And from ODU to OCU, there is an open interface called F1. This was defined by 3GPP. I'll talk about that. And then I have open central unit. And I also have other component called RIC, Radio Intelligent Controller, some AI ML related stuff coming as part of the radio itself. So the third one is the Open RAN, where interfaces are open, all the interfaces are open, the hardware is open, and it's a virtualized environment. On top of that, we are using AI ML concept also. And this particular architecture is not only for 5G, but also for 4G, for EPC or 5G, both. In case of a 4G also, this disaggregation is possible as per the standard given by 4N Alliance. So that's the basic concept of Open RAN. Let's look into slightly more detail of Open RAN, concept of Open RAN. So there are many way one can deploy a Open RAN. In the first picture here, we are talking about the BBU being divided into three products, that is RU, radio remote unit, DU, distributed unit, and CU, central unit. In this picture, they are talking about having open interfaces between RU and DU and DU and CU, and further even to the core. And we are also talking about using the open hardware for RU, for DU, right? So software and hardware are disaggregated, one. Secondly, hardware is open hardware or commercially off the shelf hardware. And of course, those software can be proprietary. There's no issue on that. Companies can make the proprietary software or open software. So three product solution. And in this solution, we are talking about virtualizing the CU onto a cloud. On an edge data center, I can deploy the central unit part of this solution. The other option discussed is like I can have RRU just like the previous one, and then I can club DU and CU together and deploy onto the edge DC itself. So I have a common hardware, virtualized one, and I can deploy DU software and CU software, and then I connect to the core network. So there can be multiple architecture possible for Open RAN depending upon your solution or company solution, one can use it. Okay, so we talked about breaking. Any question so far before I go into part 3? Any question related to part 2 or part 1? Should I go ahead?
Yes, sir.
Okay. Right.
Okay.
Thank you.
Hello, sir.
Yeah.
Ashok ji.
Ji.
One doubt. What
Yeah.
is the conversion time from antenna to for BBU into RF to optical conversion? That also includes time.
Yeah. So you were
And
saying
also
that.
for yes.
Your question is that that like there'll be some latency from RF to the DU, and there'll be some latency from DU to CU. So what kind of latencies can be supported maximum? That's the
Yes.
one question one
Yes.
can ask. And there can be other requirement that if I have an application which is URLLC, so whether a particular architecture of Open RAN is suitable or not, that could be a second question. Am I right?
Yes.
So I have 1 or 2 slides on that. So can we wait for that so that I explain you at that moment? That will be more
No
relevant.
problem. No
Okay.
problem. Thank you.
Thank you. So when we talk about this functional split of BBU into 2 product or 3 product, So it was 3GPP even before release 15 of 5G, first 5G release. They had talked about these splits in the study paper. So normally 3GPP issues, one is the specification of a certain thing and other is the study paper, right? So this was the study paper issued as part of release 14 itself, where they have talked about various radio access architecture and interfaces. So in this standard itself, they have talked about various split. So let me show you that. So as we know that BBU, which we talked about, it handles the air interface. On air interface, I think some part of it is not shown. So you handle physical layer, which is not visible to you. Then a MAC layer, RLC layer, and upper layers may handle PDCP, SDAP, RRC. So BBU handles all these layers. So if it is a single box, everything is being handled in the BBU itself. The traditional RAN or RAN up to 4G used to handle, even in 5G, we are handling in some of the architecture, everything in the BBU. But what 3GPP talked about, that we can split this BBU into multiple parts. As we saw earlier in our earlier picture, that I can have RU, I can have DU, and then I can have CU, and divide these layers into these, that RU will handle which part of the layer, CU will handle which part, or DU will handle which part. So these were defined as different options by 3GPP, like option 1, option 2, option 3, up to option 8. So looking at this picture, can you guess that in a traditional radio access network, which split I'm using? Which split I'm using? Can somebody tell me that in a traditional RAN, what I have is, on top I have just RF, and below I have BBU. So which split I'm using? Split 1, 2, 3, 4. Split is between these two, right? These two elements. So which split I'm using? Any, whether I'm using split 1, 2, 3, 4, 5, 6, 7, or 8? So answer is 8, because only the RF part 8. RF part is at the top of antenna, and the entire other things are taken over by BBU. So basically I'm using option 8 sort of in a traditional RAN. Okay, there is a possibility that in RU, suppose I have RU, suppose I have done a split into two parts. So BBU is now, let me split this into two parts, DU and CU. DU and CU. Let me do it in three parts. RU, DU, and CU. So I can decide that, okay, lower part of the physical layer, and RF, lower part of the physical layer and RF, I can put in RU. That means antenna, RF, and lower part of the physical layer is being handled at RU location. So here I'm using which option? I'm using option 7. What I'm using? Option 7 or split 7. That I have taken lower part of the physical layer and RF in the RU. And suppose in CU, I am handling RRC and PDCP layer. Suppose this I am handling at CU level. So this is option 2. So this is option 2. So CU is option 2. And whatever is remaining from here to here, that is upper part of physical layer, MAC layer and RLC layer, I am handling at DU. So this option combined is I'm using option 7 and option 2, right? Split, 2 splits I'm having. So that's why we call it split 7.2. Might have heard that split 7.2. So split 7.2 is nothing but at the RU side, I am handling lower physical part and RF. At the CU side, I am handling RRC and PDCP layer. And rest of the layer, higher part of the physical layer, MAC layer and RLC layer, I am handling at DU. So this is called split 7.2. Okay. So in case I am splitting my BBU, into RU, DU and CU, then I can use split 7.2. And this is the split recommended by ORAN Alliance. So ORAN Alliance is recommending split 7.2. Okay. Now let's talk about split 6. What is split 6? So split 6, if you talk about this one. So if I have complete physical layer and RF in RU, I have complete physical layer and RF at RU, we call it split 6. And rest can go to either DU-CU combined or DU separately and CU separately, doesn't matter. So this is called split 6. This is called split 6. So this kind of a solution, split 6 solution, is promoted by, there is an organization called SCF, Small Cell Forum. So basically they are promoting small cell architecture, and as per them, split 6 is the best option for a small cell kind of an environment. Can anybody tell me that why split 6 is beneficial for a small cell? Any idea? When we have a small cell, maybe operating on millimeter wave, the recommendation is to use split 6, that is physical layer along with RF. That at RU I'm handling the complete physical layer. Any guess why we prefer split 6 in case of a small cell?
It will enable multiplexing gain and also reduce latency.
Okay, anything else? So one of the major consideration is the backhaul requirement. That if you put say option 7.2, when you are only putting lower part of physical layer, right? So how much backhaul is required towards DU? And in case I am putting option 6, the complete physical layer, how much backhaul is the requirement towards DU or CU? So basically, in case of split 6, the backhaul requirement would be less compared to when I have some part of the physical layer at RU and some part of the physical layer at DU. You are splitting the physical layer itself. At the physical layer, your overall data rate is very, very high. So your bandwidth requirement between DU and RU will increase drastically. So in case I have a small cell, so a small cell means I have multiple cells nearby, and from every cell I have to take that backhaul. And if it is very high, That means requirement of backhaul would be very, very high. And that's why split 6 is one of the preferred uh, thing to do. There are some disadvantages also. Okay, let's move further. Okay, now let's look at overall architecture of 5G RAN, which was given by 3GPP. And then we'll discuss about what O-RAN Alliance or other organizations are talking about to make it an open RAN. So if you look at this picture, sorry, this is a picture taken from the 3GPP standard itself. What it says that you can have a monolithic RAN G node B, that is our complete BBU in a single box, right? So that is a possibility, monolithic G node B. Most of the deployment today in India is a monolithic G node B by the operators. The other architecture which is given by 3GPP for G node B is that we can split G node B into two parts, central unit and distributed unit. RF is along with the DU itself. And then we can have an open interface F1 between DU and CU. It is also possible to connect multiple DU to a single CU of G node B. So basically in 3GPP, from BBU option is that either you have a monolithic or you can divide into DU plus CU. This is what is given by 3GPP, right? So if you look at which layers will be handled at DU and which layers will be handled at CU, so that they have defined. So basically, if you look at this picture, this is Z node B being divided into DU and CU, where one CU can handle multiple DU. So the higher layer, PDCP, SDAP, and RRC, these are being handled at CU. And the distributed units, the physical MAC and RLC layer, all the three layers are being handled at DU level, right? And along with DU, we have RF. Along with DU, we have RF. So this is two-level split in case of 3GPP specifications. So if you look at where this split is, so this is the split, option 2. So if somebody asks you a question that 3GPP standard of G node B or the RAN is which split they're talking about, so they're talking about split 2 only, or option 2 of the split. 3GPP follows split 2. Okay. Now 3GPP has further disaggregated Z node B into like earlier we talked about that we have central unit and distributed unit as defined by 3GPP. This central unit is further divided into two parts. One which will handle the control plane, another which will handle the user plane. Both are central unit, but this is the signaling which will handle, this is the user data which will handle. And one CP of central unit can handle multiple user plane of central unit on an open interface called E1. And the DU, every DU will handle both control plane and user plane, and they'll have a interface F1U for user plane and F1C for control plane towards the central unit. So this is again a split architecture given by 3GPP. So 3GPP has done kind of the interfaces almost close to Open RAN, almost close to opening the RAN, right? Except that they have not talked about 3 product solution. They have talked about 2 product solution. Okay. So to support further split, which we saw that Oren Alliance is doing split 7.2. A small cell forum is trying to do split 6. Basically, they are trying to have multiple split in the physical layer itself. So up till now, what we see that this 2 split is already done by 3GPP. Now physical layer, at physical layer, can I have more split, right? Like split nomenclature given is split D, and then split E. Multiple name is given for different splits. But the CIPRI protocol, which was earlier used, is not supporting these splits. So they developed another protocol called eCIPRI. And eCIPRI is able to handle further split in the physical layer. And then you can divide RU and DU at any of these splits. So that's the concept. So let us now understand any questions so far before I proceed to next part. Or should I proceed?
Yes, sir.
Yes,
Okay.
sir.
All these decisions are by service providers only, na? Where to split, how to split, whether number of users associated. Based on that, any fluctuation takes place.
Yeah, depending upon the use case, you have to choose a particular split. And these are like this Open RAN based deployment has not happened in a big way across the globe. It is still evolving, right? So these splits are, as of now, are not very much. I was talking about most of the deployment, even in India, is a monolithic G node B. So may I request others to kindly mute your mic? Madhukar, if you can mute them. Yeah. Thank you. So let's a little bit understand about CIPRI and eCIPRI, which you said that CIPRI was an interface used earlier prior to Open RAN concept. And then in 5G and also Open RAN concept, we are using eCIPRI protocol to connect RU and BBU or RU and DU. That is also called front haul. So basically, CIPRI protocol is nothing but, I mean, its name is Common Public Radio Interface. And this was developed by industry cooperation. So at that point of time, Ericsson, Huawei, NEC, Nokia sat together and created this interface. This interface was supposed to be open interface at that point of time. Okay. And these interfaces definitions are publicly available. So you can also search on Google and have the specification of it. But its implementation was proprietary. So this Nokia, Ericsson, Samsung standard, it was a standard open interface, but implementation was done proprietary. So there was no interoperability between Nokia and Ericsson or with Samsung or Jetty or Huawei. All were proprietary implementation of CIPRI interface. So all these interfaces of CIPRI was proprietary. Now when eCIPRI got developed, this was developed by Oren Alliance. They enhanced the CIPRI one for 2 reasons. One is to make it open, and secondly to support multiple split of physical layer. So eCIPRI is a front haul of 5G and Open RAN. So basically front haul, open front haul, we call it OFH. This is nothing but eCIPRI and defined by ORAN Alliance. This is not defined by 3GPP. This is defined by O-RAN alliance. And with this, we can have packet-based front haul transport network. So in case of a CPRI, traditional CPRI, you are required to have a dark fiber. For each BTS, you need a dark fiber up to the BBU or up to the DU. But in case of a open front haul or eCPRI, I can aggregate traffic as an IP traffic and then further route. It can be Ethernet, IP, that kind of environment I can have. So more efficient, more flexible backhaul we'll have with eCPRI. So this is a picture how various split as possible. So split at every layer is possible in the eCPRI, like split between RRC and PDCP. All these splits are possible, and within physical layer, you can have multiple splits as was required. So eCPRI supports all these split. Okay, so as we have seen that in G node B, our split is at split 2, if you recall, and no further split within the physical layer. So that not the 3GPP, but kind of an open RAN and through eCPRI that has been defined. Okay, so now the one question which comes to our mind is like which option to use and what will be the backhaul requirement for each of these options. So let's take one example that what will be a backhaul requirement when I use a particular split. So suppose in this example, suppose I have 100 megahertz spectrum and I'm using 64 cross 64 MIMO. So basically with this configuration in 5G, I can achieve a maximum throughput of about 3 Gbps. When I say 3 Gbps, this is the about 3 Gbps. Slightly less would also be possible. Maybe let's assume 2 Gbps. Between 2 to 3 Gbps will be the overall throughput of a base station. Now suppose let's take an example. I have split 8. I have split 8. Split 8 is your virtualized RAN I talked about, or BBU hotel, where RF is at antenna and your BBU handling everything is 15 kilometer or 20 kilometer away. Okay, BBU. So in this case, this is the split RF at RF. In this case, although user traffic can be about 2 to 3 Gbps, but I need to have a backhaul which can support 236 Gbps, because entire RF, all the layers, all the radio signal which is handled by BBU is being transported to BBU 15 kilometer away. So the backhaul requirement is 236 Gbps. So it is not possible. It is not possible to have, and that's why if you recall, there is to be a dark fiber in case of a BBU hotel environment, which I talked about, virtual RAN environment. So there will be a requirement of very, very huge backhaul in case I use option 8. In China, they were using option 8 initially for 5G, just in a traditional way. And they were able to put this kind of backhaul. Now, if you talk about other splits, let's talk about split 7.2. What was split 7.2? 7.2 was that at RU, I have lower physical layer plus RF. So here it is. This split 7.2. So in case of a split 7.2, this one. In case of a split 7.2, since I am handling only part of the physical layer, at RU itself. So whatever goes on higher layer of physical, so I would require only 20 Gbps of backhaul to support this kind of configuration where overall throughput is 2 to 3 Gbps. So I need 20 Gbps of the backhaul from each of the BTS site. Now, in case I use split 6, you remember split 6? Split 6 is that complete physical layer is at RU. Complete physical layer is at RU. That is a split 6. So how much backhaul is required? So split 6 is here. All the physical layer with RU and MAC layer and above goes to DU and CU. So here the fronthaul requirement is only 3 Gbps. And that's why I said that in case of a small cell deployment, the suggestion is to use split 6 so that our backhaul requirement reduced drastically from say 20 Gbps to 3 Gbps. So this is one of the very important consideration to utilize which split I want to use, in 5G deployments. Any questions here? Any question? Or shall I proceed?
Sir, please proceed, sir.
Yes.
Thank you.
Yes, sir.
Thank you. Okay, now I'll talk about various Open RAN groups who are developing ORAN type of standards, which is beyond 3GPP. So there are 3 such organizations. One, we call it ORAN Alliance. ORAN Alliance is also a group of operators and other ecosystem partners who are developing ORAN related standards. The other is a group which is called TIP, TIP, Telecom Infra Project. This is led by Facebook, if you know. And the third is the Small Cell Forum, SCF, which is working on small cell related aspects of the radio. So I'll be talking a little bit about all the 3 organizations, what all they are trying to do and where they are. Starting with ORAN Alliance. So ORAN Alliance, as you know, that earlier there used to be one group called CRAN. This was a Chinese group kind of. In US and all, they had a group called XRAN. They were operators. So they merged together and created a single alliance called ORAN Alliance. So ORAN Alliance, then with these mergers, so there were 5 founding members initially. AT&T from US, then we have China Mobile, Docomo, Orange, and T-Mobile. So these were the founding members. In 2018, this was established. And then what is the mission which they want to achieve? So the mission which they want to achieve related to ORAN is that ORAN architecture should be completely open in the sense that RU, DU, CU can be purchased from different vendor and can be deployed on a virtualized environment. So all the interfaces should be open. Deployment should be possible on a virtualized environment. Then it has to be interoperable, that one RU is working to other DU and CU. And it has to be intelligent. Some AI ML stuff should be part of the radio. So these were the 4 mission of ORAN Alliance. So with this mission, their thrust area is like, first of all, to make standard. For example, eCPRI was done by them. So ORAN related specification they define. They also define architecture. Then they create an ecosystem for testing, integration, and certification. Okay, so there will be a certain testing center, certification center, where a product can be certified for interoperability or end-to-end testing and all. And then they have created a software community. So basically, along with Linux Foundation, so they have tried and created open software for RU, DU, and CU. Those are reference software anybody can use. I mean, if you are a member of ORAN Alliance, these are available to you as a member. These softwares are available to you as a member, and they allow any of the institute to become a member, contributing member. So any of you can become member of ORAN Alliance. Basically, it's very costly for other organizations, but for colleges, etc. I mean, per annum there is a cost of about 1 lakh rupees. Okay, so within this ORAN Alliance, they have created multiple working group 1, 2, 3, and every working group has certain mandate. So overall architecture is by working group 1, radio intelligent controller and other interfaces by working group 2, and so on. So specific working group are for specific purpose. In addition, they have created certain focus group and research group on different topics. You can just read. So as I talked that they have a ORAN software community where this Linux Foundation is part of that. So ORAN Alliance and Linux Foundation have come together and they have produced certain software like Open Central Unit, Open Distributed Unit, and then they have also come out with certain management and orchestration. They have developed this intelligent controller, real time and non-real time both. So they have worked on many the software related aspects, and they are trying to give it free to all their members, and they can always deploy or further improve. So what they do, what ORAN practically is doing, that they try to make standard and enforce those standards so that multiple vendor equipments are interoperable. So interoperability type of standard or enforcement of that is one of the job which ORAN Alliance does. Second is that we already know that 3GPP is making standards, and most of the standards or interfaces are open. But there may be certain area where there is no standard by 3GPP. So in those area, ORAN Alliance comes and it creates a standard where there is no standards are available. For example, this front hall specification, ECPRI. So 3GPP has not defined any front hall specification. So this was developed by ORAN Alliance. And there are many standards developed by 3GPP. Those are open standard, like X2 interface. X2 interface is between two 4G radio, 2E Node B. Those interfaces are open interface, but I have not seen that one BTS of Ericsson and one BTS of Nokia is connected and there is a handover possible. Technically, should be possible. So for all such scenario where standards are available, it creates profile for interoperability. That means one kind of a schedule which can be used to test the interoperability. Okay, so that is the work which ORAN Alliance does. And their focus is on 5G and 4G, and of course, they do some additional thing like RIC I talked about, radio intelligent controller and other aspects. As we have discussed that ORAN Alliance follow split 7.2. 7.2 means This is 7. So this is your RU that I handle lower physical part here and the RF part. At the CU, I follow split 2, option 2. So higher layer of PDCP and RRC. So this is our CU. And middle part is your DU. And that's why you call it 7.2 because option 7 and option 2 are combined. So our name given is 7.2 in case of a ORAN alliance. So what we achieve if you follow the ORAN alliance, that I can buy the radio, the RU part from multiple vendors, say vendor C, vendor B, vendor A, and I have deployed multiple number of radio across a city, across a geography. And our distributed unit can be deployed on a COTS, commercially off the shelf hardware. And that can come from, say, vendor 3, vendor 2, vendor 4, multiple vendor these may come, right? And the COTS servers may come from some other vendor. Here I'm saying as a vendor 2. So that means hardware from X vendor, software from Y1, Y2, Y3 vendors, and then I can build Open RU, Open DU, and Open CU. And of course, then I have the core at the top. So I can mix and match the equipment depending upon what works for me, what is cheaper and what is more efficient for me. So now let's look at architecture of ORAN. So this is basic architecture as provided by ORAN Alliance. So as you said, that 7.2 split. So the lower part which you see is your RU. Then you have DU here, and then here you have CU. And I just talked about, they are also talking about radio intelligent controller. So the rig park. So rig part is here. And then I have MANO, management and orchestration. And along with that, I also have non-real-time rig on the top. So if you look at this architecture, as we discussed that in OpenRU, they are handling lower part of the physical layer and RF. At DU, they are handling RLC, MAC, and higher part of physical layer. So RU and DU. CU is being deployed on a virtualized infrastructure, right, on any COTS platform. And there they are following 3GPP split of CU into two parts, CU-UP and CU-CP. So basically control plane signaling is here and user plane signaling is here, SDAP and PDCP part of user plane. This E1 interface is an open interface defined by 3GPP. The F1 interface between DU and CU is also defined by 3GPP. And between RU and DU is open front haul defined by ORAN Alliance. This is also called eCPRI. Okay. If you go on the RIC side, radio intelligent controller or RAN intelligent controller. So the real-time, near real-time component of RIC is here. So basically, the RIC helps in providing radio connection management, mobility management, quality of service management, interference management, and also it will host trained model of AIML. Trained model will be here. And even the third-party app can come. Many third-party application can come. And of course, it will have information base. All the information as a log which is coming from the network will be stored here. From this to MANO, the interface defined is A1 interface. This is again coming from the ORAN Alliance, which connects MANO. So your design, inventory, policy, configuration, all these things will be there at the top MANO layer. Along with that, you'll have the RIG part, which is non-real time. So model training can be done here. So this data will be fetched, and particular AI ML model training I can do at this one. This model is trained uh, at good enough stage, then it can come as a trend model here and can be deployed in a real-time environment. So this is a broad ORAN architecture as given by ORAN Alliance. Okay, so we in a broad form, if you see, this is the architecture. I have RU and then I have DU and CU. It can be separate, it can be combined. And then I have radio intelligent controller, which is one is real time, another is non-real time. Okay, so what are the function which RIC does is mainly the automation part. It controls and also manage. So three major function of the radio will be handled by RIC. And the RIC, as I said, there are two type. One is the near real time RIC. So basically, all the real time tasks will be done at RIC part, and there can be many apps for this purpose. We call it X app. Please remember that in a real time environment, the RIC one, there will be many third party app for different functionality, different automation, different control. We call it X app, and a non-real time RT, which is here, along with the service management orchestration, this non RT RIC is there. So there, like AI model training is one example. So here also there can be many applications, third-party applications for this non-RT RIC. We call it RApp. So please remember the difference between RApp and XApp. So RApp is at non-real-time RIC and XApp is at real-time RIC. So if you look at XApp, which is a real time along with real time RIC. So basically all the applications related to network automation will be handled at this level through the XApp. Right. And then, for example, one example is that how to manage network slicing, how to manage high bandwidth applications, how to manage prioritized communications. So all these we can have an XApp for every such management and use it, that it will manage in real time all these network slicing related aspects and other aspects. So basically it is here which will have which will manage kind of all the applications which requires latency less than 1 second. So 10 millisecond to 1 millisecond. A decision is to be taken in a network within 1 second or 10 millisecond to 1 second. So this will be handled at XApp labels. Now, if you look at RApp, so these are also for network automation, but mainly, as I discussed, that it will be a non-real time action, a kind of a model training. So with model training, I can create policies. Sorry, I can create policies or policy-based guidance using the RApps. And this is used where like latency requirement is beyond 1 second. So latency sensitive goes to the near real time, and this is handled at RF level. So this is again a high level architecture of ORAN, which we discussed in different pictures. So here they are talking about creating a open cloud on which you can deploy DU, CU, DU/CU, and OpenRU can be hardware because it has go to the top of tower. So I said that you have SMO, service management and orchestration. So this can actually manage the entire network. So there will be a connectivity to ORU, okay, on a management plane. So this connectivity is shown. Similarly, when you have DU and CU, and you also have near real-time RIC there. So the RIC connects to the SMO using the A1 interface, and your DUCU is O1 interface. With open cloud management, you can do on OT interface. So these all interfaces are O-RAN alliance defined. O-RAN alliance defined. O1, O2, A1 management plane are defined by O-RAN alliance. Now from the BTS, you have to connect to the core. So those are called NG interface, next generation interface. So that is defined by 3GPP. So there is a legend given that which is 3GPP defined, which is O-RAN defined, and like so. This particular thing is not defined by O-RAN, that how SMO can manage core. So this is not in the scope here. Okay, in a detail level, the logical architecture. So GPP interfaces, and rest of the interface relates to the 4G. If you have open RAN 4G, that I'm not covering here. So this is the logical architecture of 4G. So how the deployment will look like is like you can have an edge cloud, right? So maybe you can deploy a DU here, and you can have a regional cloud where you can deploy a CU, or you can have your own architecture. So these are some of the study which is available on O-RAN Alliance website. I have given a link. You can look at this particular white paper. Okay, the question is that why split 7.2? Why split 7.2? Okay, what are the reason to have 7.2? 7.2 means, again, I am repeating that lower physical part plus RF at RU, MAC RLC and higher physical layer at DU, and rest of the layers, higher order layers are at CU. So the first reason is that I can build a RU at low cost and simple, because it handles only the lower part of physical layer. So you can design a lower part of physical layer. It will not be very complex. So cost will also be low. That's the one reason. Second reason is that you can support massive MIMO environment with this. And third is that since part of the physical layer has moved to ODU, so we can, even the physical layer part, I'm able to deploy on a cloud. So I can do a cloudification even for part of physical layer. So these are the three regions considered to have this split 7.2. But what are the disadvantages of having 7.2? Those are like, as we had seen, that front haul, I need a very high bandwidth. For example, in my example, when I had 100 megahertz, 64 class 64 MIMO, so my front haul requirement was about 20 Gbps to support 3 Gbps of the overall data capacity. So the front haul requirement is higher. Front haul requirement would be a bit higher. So, and also a high end of fiber is required, which can support good stability and latency. So high end of fiber would be required. And third is that on DU, distributed unit, since I'm handling higher physical layer, so processing would be high, overall processing would be high. So there'll be high load on distributed unit. And then there may be a performance related issue on the DU in case you don't have enough compute or enough memory into the DU hardware. So these are kind of issues with 7.2. So you have to trade off. You have to have a trade off. So that is split 7 about. So we have talked about ORAN Alliance. Now let's talk about TIP, Telecom Infra Project, which is led by Facebook. So what they do and how they are different from ORAN Alliance. So they also have got many groups. So they are working on many aspects. Our interest is into this one, Open RAN 5G new radio. So what they are working on. So so let's first understand difference between ORAN and TIP, what they work. So ORAN, we already discussed that they develop standards where there is no standard, and interoperability is the one of the aspects. And wherever there is a standard, they create profile to test uh, interworking like X2 interface, and they focus on 5G and 4G. So these are the four major work which ORAN Alliance does. What TIP does is they focus on deployment of all 2G, 3G, 4G, and 5G. So their main aim is to develop ecosystem. So they do plug fest, they do live deployment in the field, they enable open RAN ecosystem. So they ensure different vendor software, hardware interoperate with each other. So making a productization is one of the use case. They facilitate field trial. So basically they are into developing ecosystem around whatever standard is done by ORAN Alliance. ORAN Alliance. So that's the difference between ORAN and TIP. So what they do? So to achieve this particular objective, so they take interface specifications, that is 3GPP and ORAN combined, right? So with this, they create a common minimum requirement. They create a common minimum requirement. And then based on these requirement, they encourage vendors to produce a build. So in this case, these are RU, DU, and CU, or SD-RAN, or open source. So basically, RU and DU, CU are built based on this common requirement. Then they have arrangement of test and validation, and they also issue some certification. Then they facilitate field trial and deployments. And finally, for adoption, there is a program called TIP Exchange. So that's also some sort of badge or certificate which they issue. So this is the area of work which TIP does, which is different from ORAN Alliance. So ultimately, what they're trying to achieve, that they have RU, DU, and CU. They are connected on open interface, RU-DU front hull, DU-CU mid hull, which is F1, and then from CU to the core network. So on top of these hardware, that is the open hardware, you can have RU software, DU software, and CU software. And you have API connectivity towards NMS or MANO, management purpose, and also AI/ML app, which we talked about, RIC. So this is the Open RAN reference architecture suggested by TIP, which is nothing but a common minimum standard taken from 3GPP and ORAN Alliance. So TIP Open RAN talks about disaggregating hardware and software based on 3GPP specifications, and of course ORAN. And they support open interfaces between RUDU, CUDU, and also with RIC. And they give multiple architecture option. It's not a single one, but multiple. And they support deployment either on bare metal directly on server, or on a virtualized environment, maybe VM, or on a containerized platform. And finally, they adopt newer technology like AI, ML, CI/CD, and so on. So this is the overall TIP Open RAN. So what are the different multiple architecture they follow? So the architecture which they follow is like this can be a monolithic G node B, but of course hardware and software disaggregation is there. Or I can have RU and BBU handling DU and CU together. So second type of thing. Then third, I can have RU, I can have DU, I can have CU, 3 product model. They also support that. And finally, maybe RU, DU is combined just like 3GPP and CU differently. So all those splits, all those split options are supported by TIP. So they have already developed a open RAN ecosystem. For example, if you look at different component like RU, DU, CU, OEM. So these are OEM who have actually developed along with TIP their hardware oblique software for that. Similarly, the L2 and L3 software is done by Redisys, Ultron. There is slightly old picture. Now more ecosystem has developed. Then Open RAN software like Mavenir, Altio Star, Parallel Wireless, these are the company who are into it. Similarly, L1 software is by Intel and Redisys. So they have developed like ecosystem of companies doing, somebody is doing L1, somebody is doing L2, somebody is doing L3, somebody is doing hardware, and somebody is doing software. So they have created a ecosystem of radio access network. I'm talking about it. Okay. So any question or shall I proceed? I'll see you. So basically at BTS location, they are talking about having complete physical layer like this. So we have seen 3GPP, we have seen ORAN. So small cell forum is nothing but split 6 at, that means entire physical layer along with the radio. Okay. So what they have done, so they have created like you have MAC layer and physical layer. Physical layer is at RU. So they have created an interface API between MAC layer and physical layer, and they call it FAPI. This is the work which they have done, right? And that's why you can split. It's an open standard they have created, right? So that's their idea of. So basically, they have created FAPI interface, and NFAPI is network FAPI. In case you are splitting physical and MAC layer into 2 products, you use NFAPI. In case you are not splitting, but you can have these layers, L1 and L2 layers, physical and MAC layer from different vendor. So you can use the FAPI interface to connect these two, right? So full form of FAPI is Functional Application Platform Interface. And these are freely available. So basically you can mix and match physical and MAC layer from 2 different company and use that. So that's the thing which they have done. So FAPI and NFAPI specifications are available on their website free of cost to anyone and everyone. So even if you want to develop something, you can use these standards. So I discussed about NFAPI also. So there are 4 or 5 standards which they have done it. So one of the is the main API for FAPI out of the total standard which they have done it. So basically, you can now do the physical layer entire system on a chip using this. And they have defined software stack for MAC and higher layer protocols. So these are the part of the 5G FAPI physical API specification which they have done it. So how we can use FAPI and NFAPI with all kind of architecture? Here it is shown. If you are using split 7.2, then you can use FAPI interface here because upper part of physical layer and MAC layer is with DU. So you can use an internal FAPI interface between physical and MAC layer. If you are using split 5, so then you can use FAPI here and FAPI network FAPI because you are splitting at this point. If you are using split 2, then also you can use internal FAPI. So what they're trying to say that in all the scenario you can use the FAPI interface developed by them as a NFAPI or FAPI, including the option 6 or split 6. So this is what overall SC small cell forum solution. You can have integrated solution, you can have disaggregated solution. So in integrated, you have one product, you can use FAPI internally. If you have two product solution, RU and DU, that is nothing but option 2 of 3GPP or option 6 of small cell forum. And option 7 also uses that, and option 8. And 3 product solution, which combines option 2 and 6, option 2 and 7, 7.2 or 7.6.2 or 8.2. So these options. So in all places you can use a FAPI or NFAPI interfaces. Now the last slide about why split 6, what is the benefit? So the low load on front head, we have seen that in our example of 100 megahertz spectrum, 64 cross 64, if I using split 6, my front haul requirement was only 3 Gbps compared to 20 Gbps in split 7.2 and 200 plus Gbps in split 8. So load on front haul is low in case of split 6. So small cell is the good example of using it. And then you can use any kind of front haul, Ethernet, fiber, microwave, etc. And your load on DU would also be less. And your RF testing becomes very easy because if you have physical layer also along with the radio, so testing that physical layer becomes a complex at every site. So RF testing and verification becomes easy in split 6. So and what are the issue? Issue is that your RU become complex because you have to handle physical layer. And you also face problem in coordination between the cell because of this architecture. And so basically you can use even non-ideal front haul in case of split 6. And in that case, you'll have an issue in supporting the massive MIMO. So these were issues. So basically it's a trade-off. So with this, you can read further on this particular, there is a good article by RCA, our wireless website. You can read later on. So with this, let me thank all of you for listening to this particular session. So thank you so much, and I'll open for any last minute question. I request everyone to open your videos and have a small interaction if you want. Or you can tell me whether this was interesting session, you got some information out of it, or although it was not very technical. So any comment or any feedback which you may like to give, Dr. Mallikarjun or Dr. Jawahar?
Hello, sir.
Yeah, we can.
Sir, am I
hear you.
audible? Yeah.
Yes.
Sir, all these functionalities are realized using C programming or any other specific languages?
So that's your choice. So you can use
I mean, not exactly
choice
really
of
implemented.
your program. So basically, C would possible. In C also you can do that.
Sir, in real scenario, I mean, yes, sir. In real scenario, what are the standards, the program that those are preferred or really used?
Okay, so maybe you can look at some of the open source thing which are available and see in which language they are developed. So you can wiki like 5G, Open 5GS. You can
Okay,
wiki
sir.
and see that what language they have actually used. But as such, there is no mandate. It is up to the developer to use it.
Okay, sir. Thank you, sir.
Yeah.
Okay.
Yeah. Okay, if there is no more comment or anything, we can break for today. So, Madhukar?
Yes, sir.
Thank you, sir.
Thank you.
So respected Shri Ashok Kumar sir and all participants, it's truly a pleasure to have Shri Ashok Kumar sir with us. Session by session, his contributions are shaping this FDP into a remarkable program. It truly, we can say, his contribution has made this program a very interactive and interesting also. It is a very unique endeavor by Sir, and each of his session is rich with valuable information and captivating engagement. Sir, your presentation are consistently excellent and easy to understand also. We also extend our sincere appreciation to all the participants for generously investing their time and actively engaging in the program. Your contributions enrich discussion and enhance overall experience for everyone. So I thank all of you once again. Thank you, sir. Thank you all the participants.
Thank you, everyone. Thank you, everyone, for listening to me today. Thank you so much. So tomorrow is holiday day. After tomorrow only we have to join, Madhukar. I think tomorrow 11th is an holiday. So on Friday we'll join back. Thank you. Thank you, everyone.
Thank you, sir. Thank you so much.
Thank you.
Yes, sir.
Thank you. Thank you. Bye for now.